Okay, so yeah, I have. Okay, let's wait for someone is not still connecting. I think Joshua is still connecting. Okay, so relative orientation makes use of the omega phi kappa and then the shifts. Is that okay? So more or less it's like holding something and then trying to bring it close to the other. You can keep one and move the other, or you can bring the two together. Is okay. So when you keep one fixed and move the other, we have the one projector relative orientation. Then if you move the two, they still come together. Okay, let me record. Oh, I've started recording already. Okay. Okay, so we can actually bring the two together. Also, let's not forget that we are interested in actually keeping the projectors vertical. You know, we are dealing with vertical photography, so we want to actually keep the orientation of the projectors, okay, in such a way that we have the model formed. Okay, all right. Excuse me. So relative orientation is about that. I think I'm done talking about it. We can just want to talk about nothing. Not really. Let's look at it properly. So the process of relative orientation involves the recreation of the relative angular relationships that existed at the time of photography. Okay. So the bundle of rays that are intersecting, and then so is the core, objective of relative orientation to make sure that within that three-dimensional space, I'll try to actually do something. This is really a rough something, but the light rays are actually, let's say this is the overlap region here. Is okay. So between exposure station 1, exposure station 2, okay, we want to actually turn them around, so we are actually in the office, we're trying to replace the camera with the projector. Okay, so the projector is here, the left projector, the right projector is here, and then we're trying to now rotate them using so there's rotation and there's translation, all in a bit to make sure that we have the model form. Because remember that the model formed, or the model formation, happens in this region. Is that okay? So very important for us to know that this is quite a trial, not a trial and error, but a repetitive process. In fact, what we call the empirical process is okay. So we check the values, we check for errors, test if there are errors. If there are no errors, then we move on. Now the errors that we actually interested in relative orientation are the so-called parallax in the y direction. Okay, so now remember that we've already talked about parallax, but parallax that we refer to in this context is actually the bad one. Are you okay? So parallax, X parallax is good, as I keep on saying. X parallax is a good guy, okay? But then Y parallax is what we don't want. It's the bad guy, okay? We don't want him. This one. So we are trying to get rid of the Y parallax, okay? So let's go back to it. If you get some of the things I'm saying, we can move even faster in this lecture than you ever think. All right. So now we eliminate Y parallax. So as you can see in this sentence here, we are getting rid of the Y parallax. Okay. The object of arrow is to recreate the same relative relation between diapositives that exist at the time of photography. Remember that diapositives means you are in the office. There's been a process, a photographic process to change the actual, film, if you like, that film or whatever it was that you got from the camera to the diapositive, which is actually a positive on the transparency. Are you okay? Positive image on the transparency. All right. So there you go. Everything here is just repeating what I just talked about. Okay. All right. Empirical relative orientation. Like I said, we have two of them. Is that okay? So some of the things that I talk about are already done. All right. Making use of, I think I've touched on all this already. So let's not waste time. Rotations are done such that there's an approximately zero parallax between. Okay, so I told you that the parallax is the error, and it's the Y parallax we are referring to. So everything you're looking at here, okay, everything here you can see that you see py, that is the error in the Y direction. In the X direction, the X parallax there is very useful. Is okay. In fact, there's a relation between the height of points on the ground relative to the parallax, okay, for the various points. So this, what we are looking at here is a so-called one projector relative orientation. Are you okay? So that means that it's only one projector that is moved. So we're going to talk about the two projector relative orientation. So the steps for that is what you're looking at right now. Here we have 1 as a subscript for the orientation parameters. Okay, so I'm going to talk about it. The subscripts. I have to. We need to first understand that the Y translation along the Y axis is called the Y translation or the BY. Translation along the kappa, the Z axis is actually the the delta BK. Are you okay? Delta BK. So the delta BZ. We can talk about different aspects of it. Delta BZ, delta BX, etc. Delta BX is not normally used. Is that okay? Now, so we talk about removing the parallax at different points. What are these points? You see point 2, point 1, point 4. Sorry, I should be talking about what these points are. But it seems that I rather use them before I actually tell you what they are. These are actually called the standard points. Is that okay? And so traditionally, these are points that you have on the photograph distributed like that. 1, 2, 3, 4, 5, and 6. Are you okay? All right, so you can have 9 of them. So if this is the center, then obviously you could have another one somewhere here. there, and there. Are you okay? All right. So 1 and 2 virtually are pointing to the overlap area. Are you okay? Where we have the overlap region. All right. So let's go back and then look at that. So when we say 0.2, then we know what we are talking about. Okay. Means we are referring to this 0.2 here. And then when we say 0.1 is this one, 0.3 is that one, 4, 5, and 6. Are you okay? Etc. So these are the standard points that we'll be referring to, that we'll be using. Okay, so let's go back to our material, and then so there are steps. You actually work from 1, 2, 3, 4, then you go to 6, and then check the parallax there, and then you kind of repeat. This is like an algorithm. Are you okay? But really, this is something that you did. Are you okay? With the optical mechanical instruments. Are you okay? That we are not using anymore. But then so they do relate to that, and not with the digital systems. But very good for teaching in the 2 projector empirical relative orientation. Here you can see that we are making use of, up here we are making use of just 1 projector in our bit to get rid of the parallax. And then down here we are making use of the left projector, which is projector 1, projector 2. So pay attention. Okay, so this is projector 2, projector 1, projector 2. So projector 1 is to the left. Okay, and these points that you see here, these are actually the standard points. Point 1, 2, 3, 4. Okay, and then the whole idea is that we are actually getting rid of the parallax. Okay, so if you didn't understand the topic of parallax, then you see that you're having a problem with it. Okay, so we do what we call overcorrection as at step 5. Is that okay? All right. We do the same thing as step 1, 2, 3, 4, 5. Okay, we do overcorrection. Take note of that. And then we move on. So we calculate what we call the overcorrection factor. And then that overcorrection factor helps us to carry out the 5 in both the 1 projector and in the 2 projector relative orientation. All right, so now let's look again at what I was talking about on the other side. So you can see that 0.1 is around the center area, 0.2, 0.3, 4, 5, 6. Okay, they are helping us to actually determine if there's a distortion, if there's an error. Because if you have a wire parallax, you definitely not going to have a well-formed model. You're not going to have a distortion-free model. You're always going to have a problem with your model. The model won't be well-formed. Okay, all right. So now left photograph is photo 1, which is this one, and then right photograph is this one. Okay, and then this is the actual model. Okay, so photo, and a model. Okay, so photo 1, from projector 1. Okay, then we have photo 2, projector 2, and then the 2 projectors now fuse to give you the model. Is okay. So that's the beauty of it all. All right, so what can we do with this? So the standard points, also known as the von Gruber points. I think it's just a spelling mistake. All right, these are the standard points. Okay, now let's see how the points move. So here I want you to look at the projectors like you actually look at a torchlight. Are you okay? All right. So if you have a torchlight and you have some like a transparency in which you've actually written something on. All right, so if you have your handout, the binding, you know, this blue transparency, sometimes they come in different colors. If you wrote something like on it and you actually put a torchlight on it, point it at it, it will actually project it. Because my hand is opaque, the light cannot go through it. Okay, but in any transparency, in this case, we are talking about the diapositive, which is actually a positive on the transparency. Okay, positive image on the transparency. Then we can have that projection happen. Now, that what you're seeing on the board is saying that if we actually decided to move, okay, along the our about the x-axis, then you have the omega. Okay, so now let's talk about omega phi kappa. Let's do a little bit of a recap on the omega phi kappa. So in relative orientation, it's important that we appreciate it, that if you have the projector, then there are three axes that are important. The z-axis is saying that if I rotate about the z-axis, I have the kappa. Okay, so kappa. When I say kappa 1, I'm referring to the left projector, a movement about the z-axis of the left projector. When I say kappa 2, the right projector. Okay. All right. So there you go. Let's look at omega. Undo this one. So with omega, if this is the projector, then we need to establish the x-axis. Very important. So the x-axis, the fly direction, is in the fly direction. Okay, so it means you need to rotate this way to have omega. Okay, so omega is a rotation about the x-axis. So that's the projector. All right, and that's the omega direction for you. Then the last one is the phi rotation. If you want to rotate about the phi, you need to establish what the x is. I need to know where the y-axis is, and it makes 90 degrees with it. Okay, and so that means that we are not moving this way, we're actually moving this way. Okay, so that's going to be rotation in this direction. Okay, so now I want to call that phi. It can be this way or it can be this way, but really I prefer we use this one. So this is phi. So omega phi kappa is, and you can just take any object and rotate it, and you can the omega phi kappa can take care of it. In fact, in gaming, yeah, games that people make for Android and iOS and all that, they make use of these angles. You'll be shocked that you are learning it here in photogrammetry, but the real application is in game development. Okay, so the rotation about x is called omega. Rotation about y is called phi. Rotation about z, the z-axis, is actually kappa. It's okay. The subscript 1, 2 represents the left photo and the right photo, and then the right, or the left projector and the right projector. Are you okay? All right, so that will be that. Let's go back to the material. So if you look at this, and we are looking at the effect. Are you okay? The effect of omega, if we rotate about x, then we end up moving up. Is that okay? So if you actually listen to me and you want to prove that you understand it, by now you are doing the rotation, the effect of phi. Is that okay? What would the effect of phi look like. So the effect of phi is like that. Is that okay? So here we are using the two symbols, phi, this one and then the other phi. Okay, so why is phi looking like this? Why do we seem to be having some kind of rotation? Okay, remember that we are interested in getting rid of what? The y parallax, which is along the y axis. Is okay. So every if movement has to be resolved in the y direction. Are you okay? All right. So now the y axis seems to go into the board. Are you okay? More or less. And so when you start turning about the y axis, then you are really having some kind of trapezoid. Are you okay? Effect, trapezoidal effect. Let me put it that way. So the points seem to be moving away, more towards the center, and then away from the center. You have that kind of effect. If you use a torchlight, you appreciate it. It's okay. If you turn a torchlight, you appreciate it. If you go that way, fine. But if you go that way, you have a distorted, model. The same thing happens though with the omega. But I think with the resolution, the omega moves in the x direction, and then this one goes in the y direction. Are you okay? We are rotating about x. You rotate about x, you go in the y. You rotate about y, you go in the x direction. Are you okay? That is why we are having this. Okay, so basically that is the effect of phi. The effect of kappa is like driving a car and turning the steer. Are you okay? So we are rotating like that, and then we are having one hand go up, one goes down. So that is what you are looking at. Are you okay? So it makes sense. This one is the best way to appreciate it. If you can't remember the first two, omega and phi, this one makes it easy to understand. All right. So we also have the shifts. We can have delta bx, delta by, delta b, z. Okay, so these are just shifts. So instead of you to rotate, you actually shifting along an axis. Is all right. So there you go. So you see you see by. Okay, well, even if you don't put a delta, you look at it as by is really the base component, the y component of the base, and then bx is the x component of the base. Are you okay? Along the base. All right. So the air base can be looked at in x, y, z dimensions. Are you okay? So the x component of the base, which is really the base, is the distance between the two, projectors or the two exposure stations when we're flying. Are you okay? So we can have bz being a dip like this. Bx is a shift along the x. By is a shift along the y. I think very easy to appreciate. But we're going to use the change in delta by to derive a formula as we go. So we get quite mathematical over there. All right, so we can have this one is like torchlights going up and down. I wish you could see, this table here. You can see that, maybe you can't see it, but I'll find a better way to show you. When you actually move the torchlight up and down, it reduces or increases more or less. That is what we are looking at over here. Delta bz, delta by is also a shift along the y. So you can see all points begin to move in the y direction. So that one you don't need to even think. Are you okay through it? And then delta bx, I think it's not really relevant. So we're not even talking about it. Okay, so delta bz, from a planometric point of view. So in pictures, can you see that we are shifting? Okay, along in the z direction. Okay. All right. So let's look at it. Going down. Well, I think this one is looking funny. Going down, and then we have the points moving upwards. That's quite interesting. Okay, we need to look at this again. Okay, so delta bz looks like more like this, and then we can establish a relationship between delta bz and then the change in the y coordinates, more or less the model coordinates. Are you okay? So these represent this represents the projector. These things here, they represent the projector. So before we actually shifted the projector, we have this situation, and then when we actually shift it down, we have that situation. So it's the same projector moving by a distance of delta bz. Is that okay? All right. So there we go. We are going to write a relation between delta bz, the y coordinates, and the effect of which is actually delta bz. All right. So down here in this formula, we can see that it's kind of relative. I mean, this is just simple proportion. Okay, if we move by a certain amount of delta bz, then we also have a change of delta y in the coordinates. The actual coordinate is y, okay, for the point in question, and then the z for the point in question, the model point in question. And so we can actually look at this diagram here and derive a very simple formula. Okay, so let me take this off and then try to zoom a little bit, zoom out. Okay, so when you look at the diagram up there, we can write this formula and also establish the fact that the change in the y coordinate is actually, given by this relationship minus y over z, delta bz. So here, what is interesting about it is that this is the shift that we made. And this is, okay, sorry guys, I'm hearing some noises. I was thinking it's a mouse. No, there are no mouse. There are no mice in my room, but yeah, they just scary, isn't it? They're nasty. All right, so delta y is equal to minus y over z times delta bz is a typical example of every movement that we make. Remember, we can make about 6 types of movements: 3 rotations, 3 shifts, or 3 rotations, 2 shifts. Is that okay? That are relevant. So there we go. We have done the work for you. We don't have to worry with the derivation. We can establish the fact that we have delta y, a change in y. This is the first one that we have derived. For the y, a shift in y is directly proportional to a change in the coordinate. When it's shifting the y, all the coordinates in y will change. When it's shifting, when you rotate about kappa, yeah, when you make a change in kappa, then you have this relationship. Then when you make a change, I think we've already talked about this one. When you make a change in the rotation, delta phi, we also have this relationship, IAK x, y. So where x, y, z, these are model coordinates, all right? We can also have this relationship here. So there are a few that can be combined into one long equation, IAK. So we can now combine the total effect of all the rotations and then translations that are made. Okay, so here we're not even talking about the left projector or the right projector, because we are now going to talk about left projector and then right projector by inserting 1, 2, 1, 2 and those things. Okay, so I think we find that here in the next one. When you look at this one, you can see that here we are specifically referring to the left projector for projector 1. Okay, and then we are also having the effect of projector 2. So depending on the instrument being used, then you can combine them and find the net effect. Okay, so like I told you, if I have my hand, one hand here and the other hand here, Then bringing them closer will take either one hand moving closer to the other, or the two moving a little bit, and then we get close. Are you okay? So we can deal with this the same way that we dealt with, if you remember this topic in physics, relative velocity is okay. Two cars moving in the same direction, I mean towards each other. What kind of velocity do you have? You add them up, that kind of thing. That's what you're having here in concept. That is what we are dealing with. Okay, so we can, like I said, we can combine them. This is the air base or the photo base or model base that we are looking at. Okay, this is the model base. Okay, all right. So B, and then we can reduce the coordinates here by x minus b. Is that okay? Reduce the coordinates on the right hand side by x minus b. Yeah, it's like as if you are working in one coordinate system and you're moving to another coordinate system, and you need to reduce all the coordinates by a shift. So the shift is by xb. Are you okay? Because really the difference between the left projector and the right projector, or the left model, no, the left photo and the right photo, is really the base, which is the separation between the two coordinate systems, if you like, model coordinate system. Are you okay? We have what we call model coordinates. That is what is staring at us right now. Is that okay? All right. So here, this is just some algebra, but I worry you with it. I may just take a bit of it and then put it out there, and I expect you to, understand it, appreciate it. Okay, and then answer a few questions based on it, whatever question I ask you. All right, so here we are combining. I think this one, if your algebra is good, you appreciate it. We are combining the left photo and then the effect of the left photo total parallax in x, in the left photo total parallax in y, and then we are trying to balance it out. Okay, etc. So relative orientation is really about this, about making sure that parallax goes to 0. Remember that. Is that okay? All right, it's very important for us to take note of that. In some devices, in some of the old optical mechanical instruments, they don't have a knob. In fact, the movements, the omega phi kappa, they are actually like knobs on the instrument that you turn. Are you okay? And I don't want to even, go into that bit because it's not relevant today. And yet some instruments didn't have it. So you could have it all combined into a delta omega. So we make just one movement and then the whole instrument moves about it. The two projectors will move together. So that is the effect that we are talking about here. All right. And then so on and so forth. So the last thing that we talk about in relative orientation will be the overcorrection factor, which is the fifth step in relative orientation. Okay? So the fifth step in relative orientation is to get rid of the parallax input at point 6. Are you okay? And then we go back and check at point 5 as well. All right. So here you can see that we are overemphasizing that we need to make sure that the parallax at these points are actually 0. Then we can go ahead and then derive it. So I'm not going to bore you with the derivation, but it's been actually indicated. Is okay? All right. So in terms of algebraically looking at the coordinates, you can actually look at it this way. If you assume that point 1 is here, point 2 is there, 3, 4, 5, and 6. Okay, so photo coordinates of the standard points. Okay, we could almost establish a certain relationship. Okay, anybody gives you a square, you can always come up with a set of coordinates. Between 1 and 2, we get the air base. Okay, so it's assumed that the exposure stations are at 1 in point 1 and 2. Also, we assume that we set the whole model a certain model height of z. Okay, so z is constant. And then we can also say that if the origin of the model coordinates system is actually 0, 0, and z, then obviously we can say that we can derive all the coordinates of the other points. I mean, seriously, this is just purely algebra. So x, y, z. Yes, let me just get my spotlight. This is x, this is y, this is z. So to move in the right direction, x will become 0 plus b. Then we get b, 0, z. I want you to just understand this diagram. I'm not going to, like I said, bore you with the derivations and all that. What I want you to learn in relative orientation is that you get rid of the y parallax and appreciate a few things. Omega phi kappa here. All right. So going up this way is this is x. If this direction is x, then this direction is y. Are you okay? All right. So we can now have minus y this way, positive y that way, etc. It's just generic. Are you okay? Way to represent the coordinates in the model. So there you go. Please, if you have any question, you can ask. But this meeting will end soon. I don't know whether we should be continuing, but if I actually finish up with it, I think we wouldn't need to worry too much about it. Okay. So what time were we supposed to have this lecture? What time were we supposed to have this lecture? Was it 2:30 or 4:30?
4:30.
4:30.
4:30.
Okay, all right. Because I'm supposed to have another lecture. I'm thinking I've missed the lecture. Anyway, so yeah, so that is it. This is a derivation of the so-called overcorrection factor. And so this is the overcorrection factor. I want you to just take note of this and know what it is. It is. So Z is the model coordinate Z generically for any point in the model. Okay. So remember that the photo coordinate is small letter x, y, model coordinate big X, z, y, and the relative orientation. We deal with the model. Okay. And then we can use the overcorrection factor, depending on the type of camera that is being used, we have a certain overcorrection factor. I want you to note that as well. So moving forwards, we have this situation here. So we can just say that the Z, we can actually relate the formula of overcorrection factor, with this diagram here. Okay, where your F is your Z and your small y is your actual, y. We can put it into the formula and then do a little calculation and find the overcorrection factor. So depending on the camera you are using, we have, super wide angle camera. We have wide angle camera, normal angle. You use, what determines whether it is normal angle and all those things. That's also the focal length. The focal length also determines that. So we can put that in y, and then this is actually the z up here. So z over y is the format divided by 2. So this is actually a 110, okay, by 110 format. Okay. So what is the format? The format is the dimension of the photograph. Is that okay? All right. Please just ignore some of these things, but it's just playing with the algebra, what we do with the rotations. Okay. So don't spend too much time staring at it, but just take note of them, that you appreciate what they are. That's the most important thing. Okay. All right. So that will be that. And then I think this meeting ends in 1 minute time, because I fear I probably lost a lecture. I'll end it here.
Okay, sir.
I feel I've missed one lecture, but it's okay. I'll end it here. So we will continue another time. We'll talk about absolute orientation and then area triangulation. We'll see whether we can do one or do the two. Is that okay? So have a nice weekend. If you have any question, please call me, send it through WhatsApp. Is that okay?
Oh, okay, sir.
So all the best.
Thank you, sir.
You're welcome. Have a nice weekend. Okay.
Bye bye.
Bye.